Imagine yourself floating in the vast darkness of space, watching as beams of light streak past you at incredible speeds. These photons, these tiny packets of energy, are racing through the cosmos at nearly 300 million meters per second. This is the speed of light, a cosmic speed limit that governs everything we know about the universe. But tonight, as we drift through this peaceful cosmic theater, we ask ourselves a question that has puzzled scientists and dreamers for generations. What would happen to us, to our very existence, if we could somehow match this incredible speed? Picture yourself aboard a spacecraft. Not just any spacecraft, but one capable of something that seems impossible. A vessel that could accelerate you to the speed of light itself. As you sit in the pilot's seat, watching stars transform from distant points into streaking lines of light, you might wonder about something profound. Would time itself change for you? Would the relentless march of aging that affects every living thing on Earth suddenly slow down? Or perhaps even stop completely? This question touches the very heart of what it means to be human. We age, we grow old, we watch the seasons change, and the years pass by. Time seems like such a constant, such an unchangeable force in our lives. We wake up each morning a little older than the day before. Our cells divide and age. Our hair grows grey. Our bodies slowly wear down with the passage of years. It seems as natural and inevitable as the rising of the sun. But what if time isn't as constant as we think? What if this thing we call time, this invisible force that pushes us forward from birth to death, could actually be bent, stretched, or even stopped? The idea seems like something from a science fiction story. But the more we understand about the universe, the more we realize that reality is often stranger than fiction. Tonight, we embark on a journey through some of the most mind-bending concepts in all of science. We'll explore how speed and time are connected in ways that challenge everything we think we know about growing older. We'll discover how traveling fast, incredibly fast, could theoretically allow someone to experience time differently than the rest of us. We'll delve into the possibility that the secret to slowing down aging might not be found in a medicine bottle or a fountain of youth, but in the fundamental laws that govern space and time themselves. As we begin this exploration, let yourself relax into the wonder of it all. The universe is full of mysteries that are slowly revealing themselves to us. The relationship between speed, time, and aging is one of the most fascinating puzzles we've ever encountered. Whether we could ever actually travel at the speed of light, and what it would mean for our lives if we could, these questions open doorways to understanding the very nature of existence itself. So settle in, close your eyes if you'd like, and let your mind wander through the cosmos with us. We're about to explore one of the most profound questions ever asked. If you could travel at the speed of light, would you stop aging? The answer might surprise you, challenge you, and maybe even change how you think about time itself. To understand what might happen if we could travel at the speed of light, we first need to explore something we experience every single day, yet rarely stop to truly think about. Time itself. What exactly is time? It's such a simple question, yet one that has puzzled philosophers and scientists for thousands of years. Think about your typical day. You wake up in the morning, perhaps to the sound of an alarm clock. You go through your daily routines, eat your meals, work, spend time with loved ones, and eventually fall asleep at night. Each of these activities happens in a sequence, one after another. This sequence, this ordering of events, is what we call time. It's like an invisible river carrying us forward, always in the same direction, never allowing us to go backward or skip ahead. But time is more than just a sequence of events. It's the dimension in which change occurs. Without time, nothing could move, nothing could grow, nothing could happen at all. The universe would be frozen like a photograph, with every particle, every star, every living thing locked in place forever. Time is what allows the story of the universe to unfold, page by page, moment by moment. Throughout human history, we've tried to measure and understand time. Ancient civilizations looked to the sun, tracking its movement across the sky to divide the day into manageable portions. They watched the phases of the moon to create months and observed the changing seasons to mark the passage of years. These early timekeepers recognized something profound about time, that it flows at what seems like a constant rate, carrying all of us along at exactly the same speed. We've become incredibly precise in our measurement of time. Modern atomic clocks can measure time so accurately that they wouldn't lose or gain a single second in millions of years. These clocks work by counting the vibrations of atoms, using the incredibly regular oscillations of electrons as a cosmic metronome. Yet despite our precision in measuring time, the fundamental nature of what time actually is remains one of the deepest mysteries in all of science. Now, let's think about aging, something even more personal and immediate than time itself. From the moment we're born, our bodies begin a complex dance of growth and change. As babies, we grow rapidly, our brains developing new connections, our bones growing longer and stronger. We learn to crawl, then walk, then run. Our bodies are like incredible machines, constantly building and rebuilding themselves. During childhood and adolescence, the building process dominates. We grow taller, our muscles become stronger, our brains develop the ability to think in increasingly complex ways. This is time working in our favor, helping us develop from helpless infants into capable adults. But somewhere around our mid-20s, something subtle begins to shift. The balance between building up and breaking down starts to change. But aging isn't just about growing bigger or stronger. At the most fundamental level, aging happens inside our cells, the tiny building blocks that make up every part of our bodies. Each cell in your body contains a complete set of instructions called DNA, like a library of blueprints that tell the cell how to function. Over time, these cellular blueprints can become damaged or worn out. The machinery inside our cells that reads these instructions and carries out the work of living gradually becomes less efficient. Your DNA is constantly under attack from various sources. Oxygen, the very gas we need to breathe to stay alive, creates harmful byproducts called free radicals, as our cells use it to generate energy. These free radicals are like tiny molecular bullets that can damage the delicate structure of DNA. Radiation from the sun, from cosmic rays, and from natural radioactive elements in the environment also contributes to DNA damage. Even the normal process of copying DNA when cells divide introduces small errors, like typos in a document that's been copied too many times. Imagine your cells like tiny factories. When you're young, these factories run smoothly, producing everything your body needs with remarkable precision. But as years pass, the machinery starts to show wear and tear. The workers inside the factory, the proteins and enzymes that do the actual work, begin to make more mistakes. The factory's power supply, provided by structures called mitochondria, starts to weaken. The quality control systems that usually catch and fix problems become less reliable. Your mitochondria are particularly important in the aging process. These tiny structures inside your cells are like power plants, converting the food you eat into energy your body can use. But this energy production process isn't perfect. It creates waste products that can damage the mitochondria themselves and other parts of the cell. Over time, your mitochondria become less efficient at producing energy, and your cells have less power available to carry out their functions and repair themselves. The ends of your chromosomes, called telomeres, also play a crucial role in aging. Think of telomeres like the plastic tips on shoelaces that prevent them from fraying. Every time a cell divides, the telomeres get a little shorter. When they become too short, the cell can no longer divide properly and may die or become dysfunctional. This process acts like a cellular countdown timer, limiting how many times your cells can successfully reproduce themselves. This cellular aging process affects every part of your body. Your skin becomes less elastic as the proteins that keep it firm and smooth begin to break down. Collagen, the protein that gives skin its strength and flexibility, becomes stiffer and less abundant over time. Your muscles gradually lose mass and strength as the cells that make up muscle fibers become less efficient at repairing themselves. The process of building new muscle proteins slows down, while the breakdown of existing proteins continues at the same rate. Your bones become more fragile as the balance between bone building and bone breakdown shifts over time. Throughout your life, your bones are constantly being remodeled, with old bone tissue being dissolved away and new bone tissue being laid down. In youth, the building process dominates, but as you age, the breakdown starts to outpace the building, leading to thinner, more fragile bones. Even your brain, that incredible 3-pound universe inside your skull, shows signs of aging as neurons. The brain cells that process information begin to function less efficiently. Unlike most cells in your body, most neurons can't divide and create new copies of themselves. So when brain cells are damaged or die, they're often gone forever. The connections between neurons, called synapses, may also become less efficient over time, making it harder for different parts of your brain to communicate with each other. Your cardiovascular system ages too. Your heart muscle may become stiffer and less efficient at pumping blood. Your blood vessels can develop deposits of fatty material that narrow them and make them less flexible. This reduces the efficiency with which oxygen and nutrients are delivered to your tissues throughout your body. But here's something fascinating to consider. All of this aging, all of these changes happening in your cells and tissues, they're all processes that unfold in time. Every chemical reaction that damages your DNA, every protein that gets folded incorrectly, every cellular repair that happens a little less perfectly than it did when you were younger, all of these events are tied to the passage of time. The rate at which these aging processes occur isn't the same for everyone. Some people seem to age more slowly than others, maintaining their health and vitality well into their later years. This variation suggests that aging isn't simply a matter of time passing, but depends on many factors, including genetics, lifestyle, environment, and perhaps even factors we haven't discovered yet. Scientists have observed that aging doesn't happen at the same rate in all parts of the body, or even in all types of cells. Some tissues seem to age faster than others. Some cellular processes break down earlier than others. This complexity suggests that aging is not just one process, but many interconnected processes all unfolding simultaneously as time passes. This raises an intriguing question. If time itself could somehow be slowed down, would the aging process slow down too? Think of it like a movie playing in slow motion. If you could slow down the film of your life, would all the biological processes that cause aging also slow down proportionally? Would your cells age more slowly? Would the damage to your DNA accumulate at a slower rate? Would the gradual wearing down of your body's systems take much longer to occur? The relationship between time and aging seems so fundamental, so unbreakable, that we rarely question it. We assume that getting older is just a natural consequence of time passing. But what if this assumption is wrong? What if time isn't the steady, unchanging force we think it is? What if time could actually be stretched or compressed? And what if doing so could affect how quickly we age? These questions might seem purely theoretical, like something from a fantasy story. But as we'll discover, the universe operates according to rules that are far stranger and more flexible than our everyday experience suggests. The connection between time and aging, which seems so solid and unchangeable in our daily lives, might actually be much more malleable than we ever imagined. As we drift deeper into this cosmic mystery, keep in mind that every tick of every clock, every heartbeat in your chest, every breath you take, is intimately connected to the fabric of time itself. Understanding this connection is the first step toward answering our central question about light-speed travel and aging. The journey we're taking tonight will reveal that time, aging, and the speed of light are all part of a beautiful, complex dance that governs everything in the universe. In the early 1900s, a young patent clerk in Switzerland was thinking about light, time, and motion in ways that would forever change our understanding of the universe. His name was Albert Einstein, and the ideas he developed would reveal that time, which we experience as so constant and unchanging, is actually far more flexible and mysterious than anyone had ever imagined. Before Einstein, people thought of time as universal and absolute. They believed that time flowed at the same rate everywhere in the universe. If you had a perfectly accurate clock on Earth and another identical clock on a distant star, they would always show exactly the same time, ticking away in perfect synchronization. Space was thought to be a fixed stage where events played out, and time was the universal conductor keeping everything moving at the same steady pace. But Einstein had a different vision. He realized that space and time weren't separate things at all, but were intimately connected, woven together into a single fabric that he called space-time. This wasn't just a mathematical trick or a convenient way to describe things. It was a fundamental truth about the nature of reality itself. Space and time are as connected as the length and width of a piece of paper, inseparable aspects of the same underlying structure. Einstein's special theory of relativity, published in 1905, started with a simple but profound observation about light. He noticed that the speed of light in empty space is always the same, no matter how fast you're moving when you measure it. This might not sound revolutionary, but it has absolutely mind-bending consequences. Imagine you're standing on a train platform, and a train rushes past you at 100 kilometers per hour. If someone on the train throws a ball forward at 50 kilometers per hour relative to the train, you would see that ball moving at 150 kilometers per hour. The speeds add up, which is exactly what we expect from our everyday experience with moving objects. But light doesn't behave this way. If that same train had a powerful laser pointing forward, and the laser beam shot out at the speed of light relative to the train, you wouldn't see the light beam moving faster than the speed of light. You would still measure it moving at exactly the speed of light, about 300 million meters per second. This seems impossible, but it's been confirmed by countless experiments. Einstein realized that for this to be true, something else had to be flexible. If the speed of light is always constant, then space and time themselves must be able to stretch and compress to accommodate this constancy. This led him to one of the most startling conclusions in all of science, that time is not absolute. Time can run faster or slower depending on how fast you're moving and how strong the gravitational field is around you. The faster you move through space, the slower you move through time. This isn't just a theoretical curiosity, it's a real, measurable effect that happens all around us. The difference is usually incredibly tiny, so small that we don't notice it in our daily lives, but it's always there. Every time you walk across a room, time is passing slightly slower for you than for someone sitting still. Every time you drive your car, your wristwatch is ticking just a tiny bit slower than the clocks in the buildings you pass by. This effect is called time dilation, and it becomes more pronounced the faster you go. At the speeds we encounter in everyday life, the effect is so small that it would take incredibly precise instruments to detect it. But as you approach the speed of light, time dilation becomes dramatic and impossible to ignore. Let's imagine you're aboard a spacecraft capable of traveling at 90% the speed of light. As you accelerate to this incredible speed, something remarkable happens. Time begins to slow down for you relative to people back on Earth. If you could look back at Earth through a powerful telescope, you would see people moving in what appears to be slow motion. Their clocks would seem to be running slowly. Their entire lives would appear to be unfolding at a leisurely pace. But here's the really mind-bending part. From your perspective aboard the spacecraft, everything seems completely normal. Your watch ticks at its usual rate. You age at what feels like the normal pace. You don't feel like you're moving through time slowly. It's only when you compare your experience to that of people in a different reference frame that the time dilation effect becomes apparent. Meanwhile, if the people on Earth could somehow observe you on your speeding spacecraft, they would see you moving in slow motion. Your movements would appear sluggish, your clocks would seem to run slowly, and your aging process would appear to have slowed down dramatically. From their perspective, you would be living your life in slow motion, even though you feel completely normal. Einstein's theory also revealed that gravity affects the flow of time. The stronger the gravitational field you're in, the slower time moves for you relative to someone in a weaker gravitational field. This is called gravitational time dilation, and it's been measured with incredible precision using atomic clocks. The effect is small but real. If you live on the ground floor of a tall building, time passes slightly slower for you than for someone living on the top floor, because you're deeper in Earth's gravitational well. The difference is only about 10 nanoseconds per year, but modern atomic clocks are sensitive enough to detect it. GPS satellites, orbiting high above Earth, experience time passing slightly faster than clocks on the ground, and this effect has to be corrected for the system to work accurately. Einstein's general theory of relativity, published in 1915, showed that massive objects actually warp the fabric of spacetime itself. Imagine spacetime as a stretched rubber sheet. If you place a heavy bowling ball on the sheet, it creates a depression. Smaller objects like marbles will roll toward the bowling ball, not because of some mysterious force, but because the sheet itself is curved. This is how gravity works. Massive objects like stars and planets curve space-time, and this curvature is what we experience as gravitational attraction. The curvature of space-time also affects time. The deeper you are in a gravitational well, the more space-time is curved, and the slower time passes for you. Near a black hole, where gravity is incredibly strong, time dilation becomes extreme. If you could somehow survive near the event horizon of a black hole, time would pass so slowly for you that what feels like minutes to you might be years or even centuries for someone far away from the black hole. These effects aren't just theoretical abstractions. They're fundamental features of the universe that affect everything, including the possibility of slowing down aging through high-speed travel. The time dilation that occurs at high speeds isn't just about clocks running slowly. It affects all physical processes, including the biological processes that cause aging. If you could travel at a significant fraction of the speed of light, your entire body would experience time more slowly. Your cells would divide more slowly. The chemical reactions that cause aging would proceed at a slower rate. The accumulation of damage to your DNA would happen more gradually. In essence, your biological clock would slow down, along with every other clock in your reference frame. This is the key insight that connects Einstein's theory to our question about aging and light-speed travel. Time dilation doesn't just affect mechanical clocks or electronic devices. It affects the fundamental rate at which physical processes occur, including the biological processes that govern aging. If you could travel fast enough, you could literally slow down the aging process, not through medicine or technology, but through the fundamental physics of space-time itself. But there's a catch, and it's a big one. As you approach the speed of light, the energy required to accelerate you further increases dramatically. According to Einstein's equations, it would take infinite energy to accelerate any object with mass to exactly the speed of light. This suggests that reaching light speed might be impossible for anything with mass, including human beings. However, getting close to the speed of light, while incredibly difficult with our current technology, isn't necessarily impossible. At 90% the speed of light, time would pass about twice as slowly for you as for people at rest. At 99% the speed of light, time would pass about 7 times more slowly. At 99.9% the speed of light, time would pass about 22 times more slowly. The mathematics of time dilation show us that even if we can't reach exactly the speed of light, we could potentially achieve dramatic time dilation effects by getting close enough. This opens up the tantalizing possibility that space travel at very high speeds could indeed slow down the aging process, allowing travelers to journey to distant stars and return to Earth having aged much less than the people they left behind. Einstein's revelation that time is flexible and can be stretched or compressed fundamentally changed our understanding of aging and mortality. It showed us that the rate at which we age isn't fixed by biology alone, but is also governed by the fundamental structure of space-time itself. This discovery opened up new possibilities for thinking about life, death, and the passage of time that would have seemed like pure fantasy before the 20th century. As we continue our journey through these cosmic mysteries, we're beginning to see how the seemingly impossible question of stopping aging through light-speed travel is actually grounded in some of the most well-established principles of modern physics. The universe, it turns out, is far stranger and more wonderful than our everyday experience suggests, and the relationship between speed, time, and aging is one of the most beautiful examples of this cosmic strangeness. To truly understand how traveling at incredible speeds could affect aging, we need to dive deeper into one of the most fascinating and counterintuitive phenomena in all of physics: time dilation. This isn't science fiction or wild speculation. It's a real, measurable effect that's been confirmed thousands of times through experiments and observations. The mathematics are precise, the predictions are testable, and the implications are profound. Time dilation occurs whenever there's relative motion between two observers, but the effect becomes dramatically more pronounced as speeds approach the speed of light. To understand this, imagine time itself as something that can be stretched like taffy or compressed like a spring. The faster you move through space, the more time gets stretched out for you relative to someone who's moving more slowly. Let's start with a simple example that illustrates this mind-bending concept. Imagine you have an identical twin, and you both start with perfectly synchronized atomic clocks. Your twin stays on Earth while you board a spacecraft capable of traveling at 80% the speed of light. As your spacecraft accelerates to this incredible velocity, something remarkable begins to happen to the flow of time itself. From your perspective aboard the spacecraft, everything seems completely normal. Your clock ticks at its regular pace, 1 second per second. You breathe normally, your heart beats at its usual rate, and you age at what feels like the normal pace. You don't feel like anything strange is happening to time. You can't sense the time dilation effect from within your own reference frame. But if your twin on Earth could somehow observe you through a powerful telescope, they would see something extraordinary. Your movements would appear to be happening in slow motion. Your clock would seem to be running slowly compared to theirs. If you waved at them, the wave would appear to unfold gradually and leisurely. Even the expression on your face would seem to change slowly, as if you were moving through thick syrup. Meanwhile, if you look back at Earth through your own telescope, you would see the opposite effect. Your twin and everyone else on Earth would appear to be moving in fast forward. Their clocks would seem to be running quickly compared to yours. Days and nights on Earth would flash by more rapidly than what feels normal to you. Years would seem to pass on Earth, while only months pass for you aboard your speeding spacecraft. The mathematical relationship that describes this effect is beautifully elegant. At 80% the speed of light, time passes about 60% as fast for the traveler compared to someone at rest. This means that for every 10 hours that pass on Earth, only 6 hours pass for you on the spacecraft. The difference becomes more dramatic as you approach closer to light speed. At 90% the speed of light, time dilation becomes even more pronounced. Time would pass at only about 44% the normal rate for the traveler. For every year that passes on Earth, the high-speed traveler would experience only about 5 months. The traveler would age 5 months, while everyone on Earth ages a full year. As we push even closer to the speed of light, the time dilation effects become truly extraordinary. At 99% the speed of light, time passes at only about 14% the normal rate for the traveler. This means that 1 year of the traveler's time corresponds to about 7 years of Earth time. The traveler would age 1 year while people on Earth age 7 years. At 99.9% the speed of light, the effect becomes even more dramatic. Time would pass at only about 4.5% the normal rate. 1 year for the traveler would equal about 22 years on Earth. The high-speed traveler would celebrate 1 birthday while their Earth-bound friends and family age more than 2 decades. These aren't just mathematical curiosities. Time dilation has been measured and confirmed in countless experiments. Scientists regularly observe it in particle accelerators, where subatomic particles traveling at very high speeds live longer than they should according to their normal lifespans. Particles that would normally decay in microseconds can survive much longer when they're moving at speeds close to the speed of light, because time dilation slows down their internal processes. The most famous illustration of time dilation is the twin paradox, a thought experiment that Einstein himself helped develop. In this scenario, one twin stays on Earth, while the other takes a round-trip journey to a distant star at very high speed. When the traveling twin returns to Earth, they discover that they've aged much less than their Earth-bound sibling. Let's walk through a specific example of the twin paradox to see how it would work in practice. Imagine twins named Alex and Jordan, both 25 years old, when the experiment begins. Alex boards a spacecraft and travels to a star 20 light-years away at 90% the speed of light. The journey to the star takes about 22 years as measured by clocks on Earth, and the return journey takes another 22 years, for a total trip time of about 44 years. But because of time dilation, Alex experiences the journey very differently. From Alex's perspective, the trip to the star takes only about 10 years, and the return trip takes another 10 years, for a total journey time of about 20 years. When Alex returns to Earth, Alex has aged 20 years and is now 45 years old. Jordan, who stayed on Earth, has experienced the full 44 years. Jordan is now 69 years old, 24 years older than Alex. The traveling twin has aged much more slowly than the Earth-bound twin, not because of any medical intervention or life extension technology, but purely because of the fundamental physics of space-time. This age difference isn't just apparent or illusory, it's real and permanent. Alex has literally experienced fewer years of life than Jordan. Alex's cells have undergone fewer division cycles. Alex's DNA has accumulated less damage from cosmic radiation and normal metabolic processes. Alex's biological systems have had less time to wear down and show signs of aging. The twin paradox reveals something profound about the nature of aging itself. Aging isn't just about the passage of time, in some abstract sense. It's about the passage of proper time, the time experienced by the aging organism itself. When you slow down proper time through high-speed travel, you slow down all the physical processes that contribute to aging. But the twin paradox also raises some puzzling questions. If motion is relative, why doesn't Jordan appear to age more slowly from Alex's perspective? The answer lies in the fact that the situation isn't perfectly symmetrical. Alex experiences acceleration and deceleration during the journey, while Jordan remains in a single inertial reference frame the entire time. It's these periods of acceleration that break the symmetry and ensure that Alex ends up younger than Jordan when they reunite. Time dilation affects every aspect of biology: your heartbeat, your breathing, the firing of neurons in your brain, the replication of DNA, the production of proteins, the repair of cellular damage. All of these processes would slow down proportionally if you were traveling at very high speeds. You wouldn't notice this slowdown from your own perspective, because your consciousness and perception would also be slowed down by the same factor. From the outside, a high-speed traveler would appear to be living life in slow motion. Their movements would be languid and graceful. Their speech would sound low-pitched and drawn out. Their aging process would unfold at a fraction of the normal rate. They would be like a person in a slow-motion movie, experiencing every moment more gradually than the rest of us. This has fascinating implications for space exploration and the possibility of interstellar travel. Even with our current understanding of physics, which suggests that faster-than-light travel is impossible, time dilation offers a potential solution to the problem of vast cosmic distances. A traveler moving at very high speeds could reach distant stars within their own lifetime, even if the journey takes many decades or centuries, as measured by Earth clocks. Consider a journey to Proxima Centauri, the nearest star to our Sun, which is about 4.25 light-years away. At 99% the speed of light, the journey would take about 4.5 years as measured on Earth, but only about 8 months as experienced by the traveler. The traveler could make the round trip in less than 2 years of their own time, while about 9 years would pass on Earth. For more distant destinations, the time dilation effects become even more beneficial for the traveler. A journey to the center of our galaxy, about 26,000 light-years away, would take over 26,000 years as measured on Earth, even at 99% light speed. But for a traveler at that speed, the journey would take only about 3,700 years of subjective time. At 99.99% light speed, the same journey would take only about 260 years of traveler time. These examples show how time dilation could theoretically allow human beings to travel to distant parts of the galaxy within a single lifetime, at least from the traveler's perspective. The cost would be that many generations would pass on Earth during the journey, but the traveler themselves could survive the trip and arrive at their destination having aged only a fraction of the time that passed on their home world. The biological implications are staggering to consider. A person who embarked on such a journey would essentially be traveling into the future. They would age normally according to their own biological clock, but when they arrived at their destination or returned to Earth, they would find a world that had aged much more than they had. They would be biological time travelers, preserved in youth by the physics of high-speed motion. This isn't magic or wishful thinking. It's a direct consequence of Einstein's well-established theories, confirmed by decades of experimental evidence. Time dilation is as real and fundamental as gravity or electromagnetism. It governs the behavior of everything in the universe, from subatomic particles to massive stars, and it could potentially be harnessed to slow down the aging process for future space travelers. As we continue to explore these cosmic possibilities, we're seeing how the seemingly impossible dream of slowing down aging through high-speed travel is actually grounded in solid scientific principles. The universe has provided us with a mechanism for time travel into the future, and that mechanism could theoretically allow us to extend our lives by slowing down the very passage of time itself. As we venture deeper into the realm of cosmic possibilities, we arrive at the ultimate question that has captivated physicists and dreamers alike for over a century. What would actually happen if somehow, impossibly, a human being could reach the speed of light itself? This question takes us to the very edge of known physics. where mathematics becomes infinite and our understanding of reality reaches its limits. To explore this question properly, we need to understand why reaching the speed of light seems impossible in the first place. According to Einstein's special theory of relativity, as any object with mass approaches the speed of light, several things happen that make further acceleration increasingly difficult and ultimately impossible. First, the object's mass appears to increase from the perspective of outside observers. This isn't because the object is somehow gaining matter, but because the relationship between energy and mass becomes more complex at high speeds. As you approach light speed, it takes more and more energy to achieve smaller and smaller increases in velocity. The energy requirements grow without limit as you get closer to that ultimate cosmic speed limit. Imagine trying to push a shopping cart that gets heavier the faster you make it go. At first, when the cart is moving slowly, a gentle push increases its speed noticeably. But as the cart moves faster, it seems to become heavier and heavier, requiring enormous effort to achieve even tiny increases in speed. Eventually, the cart would become so heavy that no amount of force could make it go any faster. This is analogous to what happens when you try to accelerate matter to the speed of light. The mathematics of this effect are precise and unforgiving. To accelerate even a single electron to exactly the speed of light would require infinite energy. For something as massive as a human being, the energy requirements would be incomprehensibly vast. All the energy in the observable universe wouldn't be nearly enough to accelerate a person to light speed. This suggests that reaching the speed of light is not just difficult or impractical, but fundamentally impossible for any object that has mass. But let's engage in a thought experiment and imagine that somehow, through some unknown physics or technology, this barrier could be overcome. What would happen to time itself if a person could actually reach the speed of light? The answer takes us into territory where our normal understanding of physics begins to break down. According to the time dilation equations, as speed approaches the speed of light, time dilation approaches infinity. At 99% light speed, time passes about 7 times more slowly. At 99.9%, time passes about 22 times more slowly. At 99.99%, time passes about 70 times more slowly. The pattern continues, with time dilation growing larger and larger as speed gets closer and closer to light speed. At exactly the speed of light, the mathematics suggests that time dilation would become infinite. This would mean that time would completely stop for the traveler. From the perspective of outside observers, the light-speed traveler would be frozen in time, like a statue suspended in space. Every process in their body, every thought in their mind, every beat of their heart would be stopped completely. From the traveler's own perspective, the situation becomes even more bizarre and difficult to comprehend. If time stops completely for you, do you still experience anything at all? Would consciousness itself cease to function? Or would you experience some strange, timeless state that's impossible to imagine from our normal time-bound perspective? Some physicists have speculated that at the speed of light, the traveler might experience all of eternity in a single instant. Others suggest that the very concept of experience or consciousness might become meaningless when time stops flowing. It's possible that reaching light speed would be equivalent to stepping outside of time entirely, entering a realm where cause and effect, memory and anticipation, past and future cease to have meaning. The aging process, which depends on the passage of time and the progression of biological processes, would presumably stop completely. If time stops, then aging stops. The light-speed traveler would neither grow older nor younger. They would exist in a perfect state of temporal suspension, unchanging and eternal. But this raises profound questions about the nature of life itself. Is a being whose time has stopped completely still alive in any meaningful sense? They wouldn't be dead, because death implies a change of state, and no changes can occur when time is stopped. They would exist in a liminal state between life and death, frozen at the exact moment they reached light speed. From the perspective of the outside universe, such a traveler would become a permanent fixture of space-time. They would continue moving through space at the speed of light forever, unchanging and eternal. They would outlast stars, galaxies, and perhaps even the universe itself, because their internal time would never advance. This scenario assumes that it's somehow possible to reach exactly the speed of light, But what about getting arbitrarily close to it? As we approach closer and closer to light speed, time dilation becomes more and more extreme, but it never quite reaches infinity. At 99.99999%, the speed of light, time might pass thousands of times more slowly, but it would still be passing. At such extreme speeds, the aging process would slow to an almost imperceptible crawl. A traveler at this speed might age one day while centuries pass in the outside universe. They could potentially witness the rise and fall of civilizations, the birth and death of stars, the gradual evolution of galaxies, all while aging only slightly themselves. This brings us to another fascinating aspect of approaching light speed, the dramatic shortening of distances that the traveler would experience. Due to an effect called length contraction, distances in the direction of travel appear to shrink as speed increases. At very high speeds, the entire observable universe would appear to compress into a thin disk ahead of the traveler. A person traveling at 99.99% the speed of light toward a star, 100 light-years away, would experience that distance as only about 1 light-year. The journey that would take 100 years at light speed would subjectively feel like a 1-year journey to the traveler. Combined with time dilation, this means the traveler could cross vast cosmic distances in what feels like reasonable amounts of time, even though centuries or millennia pass in the outside universe. But there's another consideration we must address when thinking about light-speed travel and its effects on aging, the question of what happens to matter itself at such extreme speeds. As an object approaches light speed, not only does its apparent mass increase, but it also experiences enormous stresses and forces. The human body is not a rigid object, but a complex biological system made up of trillions of cells, all held together by relatively weak chemical bonds. The forces involved in accelerating to near light speed would likely tear apart any known material, let alone something as delicate as living tissue. Long before reaching light speed, a human traveler would face challenges that make the question of aging seem secondary to the question of survival. There's also the issue of energy and heat. The process of accelerating to such incredible speeds would require managing enormous amounts of energy. Converting this energy efficiently without producing lethal amounts of heat or radiation would be an almost impossible engineering challenge. The traveler might need to be protected by technology so advanced that it's essentially indistinguishable from magic by our current standards. Even if these practical challenges could somehow be overcome, there are deeper questions about what it means to be human at the speed of light. Our consciousness, our memories, our sense of identity are all processes that unfold in time. If time stops or nearly stops, do we remain ourselves in any meaningful sense? Perhaps the most profound implication of light-speed travel is not that it would stop aging, but that it would fundamentally transform the nature of existence itself. A light-speed traveler wouldn't just be a person who ages slowly. They would be something entirely new, a being whose relationship to time and space is unlike anything we can currently comprehend. This transformation might be irreversible. Once someone reaches light speed and steps outside the normal flow of time, it's unclear whether they could ever return to normal existence. They might become permanent exiles from the time-bound world of ordinary matter and energy, forever separated from the universe of their birth. The question of whether hitting light speed would stop aging thus becomes part of a larger question about the nature of identity, consciousness, and what it means to be alive. The answer might be that yes, aging would stop, but at the cost of everything else that makes life recognizable and meaningful. As we contemplate these mind-bending possibilities, we're reminded that the universe operates according to laws that often defy our intuition and challenge our deepest assumptions about reality. The speed of light isn't just a number or a limit, it's a boundary between the familiar world of everyday experience and a realm where time, space, and causality behave in ways that push the limits of human understanding. Whether anyone will ever approach this cosmic boundary remains an open question, but exploring the theoretical possibilities helps us appreciate the strange and wonderful nature of the universe we inhabit. The dream of conquering aging through speed takes us to the very edge of physics, where science and philosophy meet in contemplation of the deepest mysteries of existence. Now we arrive at the heart of our cosmic mystery. We've explored the physics of time dilation and the theoretical impossibility of reaching light speed, but what would actually happen to the human body, to the intricate biological machinery that keeps us alive. If we could somehow approach or reach these incredible velocities, the answer requires us to think about aging not just as the passage of time, but as a complex symphony of biological processes, all dancing to the rhythm of physics itself. To understand how light-speed travel might affect aging, we need to first appreciate that aging isn't a single process, but rather thousands of interconnected biological mechanisms, all unfolding simultaneously within your body. Every second, millions of chemical reactions occur in your cells. DNA is copied, proteins are assembled, energy is produced, waste products are removed, and cellular damage is detected and repaired. All of these processes happen according to the laws of physics and chemistry, which means they're all subject to the effects of time dilation. When we talk about slowing down aging through high-speed travel, we're really talking about slowing down every single biological process in your body. Imagine your body as an incredibly complex clock, not just one clock, but billions of tiny molecular clocks all ticking away in perfect synchronization. At high speeds, all of these clocks would slow down together, maintaining their relative timing while operating at a fraction of their normal speed. Let's consider what this would mean for the fundamental processes of cellular aging. One of the primary causes of aging is the accumulation of damage to DNA over time. This damage comes from many sources, including radiation, chemical reactions within the cell, and simple copying errors that occur when DNA replicates. Under normal circumstances, this damage accumulates steadily throughout your lifetime, contributing to the gradual decline in cellular function we call aging. But in a high-speed reference frame, where time is dilated, these damaging processes would occur much more slowly. Cosmic radiation would still hit your DNA, but from your slowed-down perspective, it would hit much less frequently. The chemical reactions that produce harmful free radicals would still occur, but at a greatly reduced rate. The cellular machinery that copies DNA would still make occasional mistakes, but these errors would accumulate much more gradually. From the perspective of an outside observer, a person traveling at near light speed would appear to be aging in extreme slow motion. Their hair would grow so slowly that it would appear almost frozen. Their fingernails would extend at an imperceptible rate. The lines and wrinkles that normally develop over decades would take centuries to form. Their entire aging process would unfold like a movie played at a fraction of normal speed. But here's where the biology becomes truly fascinating. The traveler themselves wouldn't feel like they were aging slowly. From their own perspective, time would seem to pass normally. They would feel like they were aging at the usual rate, because their consciousness, their perception of time, and their biological processes would all be slowed down by exactly the same factor. Their subjective experience of aging would feel completely normal. This creates an extraordinary paradox. The traveler would feel like they're living a normal lifespan, experiencing the usual progression from youth to middle age to old age. But when they compared their aging to the outside universe, they would discover that their entire subjective lifetime corresponded to perhaps just a few years or even months of external time. They could live what feels like a complete human life, while the rest of the universe ages only slightly. The cellular implications are profound. Consider the process of cellular division, which normally occurs on regular cycles throughout your body. Different types of cells divide at different rates. Skin cells might divide every few weeks, while some cells in your liver divide every year or more. In a time-dilated reference frame, these division cycles would be stretched out proportionally. A cell that normally divides every month might take years to complete a single division cycle as measured by outside observers. This dramatic slowing of cellular division could have significant implications for cancer risk. Cancer essentially occurs when cells begin dividing uncontrollably, ignoring the normal signals that tell them when to stop. If cellular division is slowed down by time dilation, the development of cancer might also be slowed down proportionally. A cancer that might normally develop and become dangerous over a period of years could take decades or centuries to reach the same stage in a time-dilated reference frame. The implications extend to every aspect of human physiology. Your cardiovascular system would operate in slow motion, with your heart beating perhaps once every few minutes as measured by outside observers, yet feeling perfectly normal to you. Your respiratory system would cycle incredibly slowly, with breaths taking what appears to be hours from an external perspective. Your digestive system would process food at a glacial pace, yet you would feel like you're eating and digesting normally. Your nervous system presents particularly fascinating questions. The speed at which electrical signals travel along your nerves would be slowed down, along with everything else. This means that your reaction times would appear incredibly slow to outside observers, yet feel completely normal to you. A conversation that feels normal to you might appear to an outside observer like an exchange between people speaking in extreme slow motion, with each word drawn out over minutes or hours. Your brain, that 3-pound universe of electrical and chemical activity, would continue to function, but at a dramatically reduced pace. The firing of neurons, the formation of new memories, the processing of thoughts and emotions, all would occur much more slowly from an external perspective. Yet from your own point of view, your mind would work exactly as it always has. You would think, feel, and remember at what seems like a normal pace. This raises intriguing questions about the nature of consciousness itself. If your brain is operating in slow motion, relative to the outside universe, does that mean your consciousness is also slowed down? Would you be aware of thinking more slowly, or would your subjective experience of thought remain unchanged? Most physicists believe that your inner experience would feel completely normal, because the rate of your consciousness would be slowed down by exactly the same factor as all your other biological processes. The process of memory formation adds another layer of complexity. Memories are formed through physical changes in your brain, involving the strengthening and weakening of connections between neurons. These changes occur through molecular processes that would be subject to time dilation like everything else. This means that memory formation would occur more slowly in absolute terms, but at a normal pace relative to your subjective experience of time. Consider the implications for learning and intellectual development. If you spent what felt like years studying and learning while traveling at near light speed, you could accumulate vast knowledge and experience, while very little time passed in the outside universe. You could become incredibly wise and knowledgeable during a journey that takes only months or years of external time. This could represent a new form of human development, allowing individuals to achieve levels of learning and wisdom that would normally require many decades. The hormonal systems that regulate growth, development, and aging would also be affected. The production and release of hormones like growth hormone, thyroid hormones, and reproductive hormones would all occur more slowly. This could effectively pause or dramatically slow down processes like puberty, menopause, and the gradual hormonal changes associated with aging. A traveler could potentially maintain the hormonal profile of a young adult for what amounts to centuries of external time. Your immune system would operate in the same slow motion as everything else. White blood cells would patrol your body and respond to threats at a reduced pace, yet this slower response would be matched by an equally reduced rate of infection and disease progression. Viruses and bacteria that might normally cause rapid illness would find themselves operating in the same time-dilated environment as your immune defenses, maintaining the normal balance between pathogen and host. The implications for wound healing are particularly interesting. The complex process of tissue repair, involving inflammation, cell division, and tissue remodeling, would all occur much more slowly. A cut that might normally heal in a week could take months or years to heal as measured by outside observers, yet feel like it's healing at a normal pace to the injured traveler. Perhaps most remarkably, the gradual wearing down of your body's systems that we associate with aging would be dramatically slowed. The slow accumulation of damaged proteins, the gradual loss of muscle mass, the progressive stiffening of joints and blood vessels, all of these age-related changes would unfold over much longer periods of external time. You could potentially maintain the physical condition of a young adult for centuries as measured by the outside universe. This biological time dilation could theoretically allow humans to outlive not just their normal lifespan, but entire civilizations, geological epochs, and even astronomical events. A person who embarked on a near light-speed journey could potentially return to Earth to find that millions of years had passed, while they had aged only decades. They would be a living bridge between different eras of cosmic history. Yet this extraordinary longevity would come with profound costs and challenges. The traveler would be forever separated from the normal flow of human time. Everyone they had ever known would be long dead by the time they returned. The society and culture they left behind would have evolved beyond recognition. They would be eternal wanderers, unstuck in time, able to witness the unfolding of cosmic history but unable to participate in the normal rhythms of human life. The biological reality of light speed travel thus presents us with a paradox. It could theoretically grant a form of immortality, allowing the human body to persist far longer than normally possible. But this biological immortality would be achieved at the cost of social and cultural mortality, separating the traveler from the human community in ways that might be more profound than death itself. As we contemplate these possibilities, we're reminded that the question of aging and light speed travel isn't just about biology or physics, but about what it means to be human in a universe where time itself can be manipulated. The biological effects of time dilation could indeed slow aging to an almost imperceptible crawl, but they would also transform the very nature of human existence in ways we're only beginning to understand. As we've explored the tantalizing possibility of slowing aging through high-speed travel, we must now confront the harsh realities that make such journeys seemingly impossible with our current understanding of physics. The universe, for all its strange and wonderful properties, appears to have built-in safeguards that prevent matter from reaching the ultimate cosmic speed limit. Understanding these limitations helps us appreciate both the elegance of physical laws and the incredible challenges that would need to be overcome to make light speed travel a reality. The most fundamental barrier to light speed travel lies in Einstein's famous equation: energy equals mass times the speed of light squared. This deceptively simple formula reveals something profound about the relationship between matter and energy. As any object with mass approaches the speed of light, the energy required to accelerate it further increases without limit, approaching infinity as the speed approaches light speed. To understand this better, imagine trying to push a car that becomes heavier the faster it goes. At low speeds, a gentle push might increase the car's velocity noticeably. But as the car speeds up, it seems to gain weight, making each additional increment of speed require more effort. Eventually, the car would become so heavy that no amount of force could make it go faster. This is analogous to what happens when matter approaches light speed, except the effect is far more dramatic than our simple analogy suggests. Let's consider some specific numbers to illustrate just how extreme these energy requirements become. To accelerate a single kilogram of matter to 90%, the speed of light would require about 2.3 times 10 to the 17th joules of energy. This is roughly equivalent to the energy output of a large nuclear power plant running continuously for about 8 years. And that's just for 1 kilogram, less than the mass of a small textbook. To accelerate a 70-kilogram human being to 90% light speed would require about 1.6 times 10 to the 19th joules. This is approximately equal to the total energy consumption of the entire United States for about 4 months. The energy requirements are so vast that they challenge our ability to even comprehend them in practical terms. But the situation becomes far worse as we approach closer to light speed. To reach 99% light speed, that same 70-kilogram person would require about 5.1 times 10 to the 19th joules, roughly equivalent to the total annual energy consumption of the entire world. At 99.9% light speed, the energy requirement jumps to about 1.6 times 10 to the 21st joules, more energy than the sun produces in several seconds. As we push even closer to the cosmic speed limit, the energy requirements grow without bound. At 99.99% light speed, we would need about 5 times 10 to the 21st joules. At 99.999%, the requirement becomes about 1.6 times 10 to the 22 joules. The pattern continues, with each additional 9 in the percentage requiring roughly 10 times more energy than the previous level. To reach exactly 100% light speed would require infinite energy, which is clearly impossible. This isn't a limitation of our technology or engineering capabilities. It's a fundamental feature of the universe itself. The laws of physics appear to absolutely forbid matter with mass from reaching light speed, no matter how advanced our technology becomes. But even if we could somehow generate these enormous amounts of energy, we would face equally daunting challenges in applying that energy safely to accelerate a human being. The human body is incredibly fragile compared to the forces involved in near-light speed travel. The acceleration required to reach such speeds quickly would instantly crush any living organism. Consider that a typical car accident might subject a person to accelerations of 10 to 50 times Earth's gravity, and such forces are often fatal. To reach 90% light speed in a reasonable amount of time, say 1 year, would require sustained accelerations of about 10 billion times Earth's gravity. No known material, let alone living tissue, could withstand such forces. Even if we spread the acceleration over much longer periods to reduce the G-forces, we would face other insurmountable challenges. The longer the acceleration period, the more energy must be carried along for the journey, increasing the mass that must be accelerated and thus increasing the energy requirements. This creates a vicious cycle where longer acceleration times lead to higher energy requirements, making the journey even more difficult. There's also the fundamental problem of where this energy would come from. Chemical fuels like those used in current rockets contain nowhere near enough energy per unit mass to achieve significant fractions of light speed. Even nuclear fusion, the process that powers the sun, releases only about 0.7% of the rest mass energy of the fuel. To carry enough fusion fuel for a light-speed journey would require a spacecraft so massive that accelerating it would require even more fuel, creating another impossible spiral of energy requirements. Nuclear reactions involving antimatter can theoretically convert 100% of mass into energy, making them the most efficient possible fuel. But even a perfect antimatter rocket faces fundamental limitations. The energy required to accelerate matter to near light speed is so enormous that the fuel would constitute the vast majority of the spacecraft's mass, leaving little room for payload or life support systems. The rocket equation, derived from conservation of momentum, tells us that to achieve very high velocities, the mass of fuel must be exponentially larger than the mass of the payload. For journeys approaching light speed, the fuel requirements become so large that they exceed the mass of observable matter in the entire universe. This mathematical reality suggests that traditional rocket propulsion, no matter how efficient, cannot achieve light-speed travel. But perhaps the most fundamental limitation isn't energetic but thermodynamic. Accelerating matter to high speeds inevitably generates enormous amounts of heat. This heat must be radiated away to prevent the spacecraft and its occupants from being vaporized. But as speeds increase, the efficiency of heat radiation decreases due to relativistic effects, while the heat generated increases dramatically. At some point, it becomes impossible to radiate heat fast enough to prevent catastrophic overheating. The challenge extends beyond just reaching light speed to the question of what happens during the journey. A spacecraft traveling at near light speed through interstellar space would encounter cosmic dust, gas molecules, and radiation. At such enormous velocities, even the tiniest particles would impact the spacecraft with tremendous energy. A single hydrogen atom hitting a near light speed spacecraft would release energy equivalent to a significant explosion. The cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space, would also become a serious hazard. Due to relativistic effects, this normally harmless radiation would be blue shifted to much higher energies for a near light speed traveler, potentially becoming lethal gamma radiation. The faster the spacecraft travels, the more intense this radiation would become. These practical challenges have led some physicists to propose alternative approaches that might circumvent the limitations of conventional acceleration. One such concept is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Rather than accelerating matter to light speed, this theoretical device would compress space in front of a spacecraft and expand space behind it, creating a bubble of warped spacetime that could theoretically move faster than light. The Alcubierre drive would allow the spacecraft itself to remain stationary within its bubble of warped space, avoiding the energy and acceleration problems of conventional propulsion. The space around the craft would do the moving, carrying the spacecraft along like a surfer riding a wave. From the perspective of someone inside the bubble, they would never experience acceleration and would not be subject to time dilation effects. However, the Alcubierre drive faces its own seemingly insurmountable challenges. The amount of exotic matter with negative energy density required to create such a space-time bubble is estimated to be equivalent to the mass energy of Jupiter. Even more problematically, such exotic matter may not exist in nature, and if it does exist, we have no idea how to create or manipulate it. Recent refinements to the Alcubierre concept have reduced the energy requirements somewhat, but they remain far beyond anything achievable with known physics and technology. Some versions of the drive might require only the mass energy of Voyager 1, but they still depend on exotic matter that may be impossible to obtain. Another theoretical possibility involves the use of traversable wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. If such wormholes could be created and stabilized, they might allow instantaneous travel between distant points without the need for high-speed acceleration. However, like the Alcubierre drive, wormholes would likely require exotic matter with properties that may not exist in our universe. Even if these exotic propulsion methods could somehow be realized, they might not provide the aging benefits we've been discussing. The Alcubierre drive, for instance, would not subject its passengers to time dilation because they would remain stationary within their bubble of warped space. Travelers using such a device would age normally during their journey, arriving at their destination having experienced the full passage of time. The mathematical and physical barriers to light-speed travel are so formidable that many physicists consider it not just impractical but fundamentally impossible. The universe seems to have been designed with built-in speed limits that prevent matter from reaching light speed, no matter how clever our engineering or how advanced our technology becomes. Yet the very existence of these limits reveals something beautiful about the structure of reality. The cosmic speed limit isn't an arbitrary restriction, but a fundamental feature that helps maintain the consistency and causality of the universe. Without this limit, effects could precede causes, time travel paradoxes could arise, and the logical structure of reality could break down. The impossibility of reaching light speed doesn't diminish the wonder of what we've discovered about time dilation and its potential effects on aging. Even speeds that are far below light speed could still produce significant time dilation effects. A spacecraft traveling at 50% light speed would experience time passing at about 87% the normal rate, while 90% light speed would slow time to about 44% of normal. These more modest speeds, while still requiring enormous technological advances, are not obviously forbidden by the laws of physics. They would still require unprecedented amounts of energy and revolutionary advances in propulsion technology, but they don't face the absolute mathematical barriers that prevent reaching light speed itself. As we contemplate these limitations, we're reminded that the universe operates according to laws that are both more flexible and more restrictive than our everyday experience suggests. While time dilation opens up the tantalizing possibility of slowing aging through high-speed travel, the practical barriers to achieving such speeds are so enormous that they may forever remain in the realm of theoretical possibility rather than practical reality. As we venture beyond the realm of light-speed travel and its effects on aging, we enter perhaps the most mind-bending territory in all of physics, the possibility of time travel itself. The relationship between high-speed motion and the flow of time opens doorways to questions that challenge our most fundamental assumptions about causality, free will, and the nature of reality. Could breaking the cosmic speed limit allow us not just to slow aging, but to move freely through time itself? The connection between speed and time travel emerges naturally from Einstein's theories of relativity. We've already seen how traveling at high speeds can slow down your personal timeline relative to the rest of the universe, effectively allowing you to travel into the future. A person who travels at near light speed for what feels like a year could return to Earth to find that decades or centuries have passed. This is genuine time travel into the future, achieved through the manipulation of space-time itself. But what about traveling into the past? This is where our exploration takes us into territory that pushes the boundaries of known physics and ventures into realms that may be forever beyond human reach. The mathematics of relativity suggest some startling possibilities, but they come with equally startling paradoxes and impossibilities. According to Einstein's equations, if an object could somehow travel faster than light, it would experience what physicists call time-like separation from events in its past. This means that the mathematical relationship between cause and effect would break down in ways that could theoretically allow the traveler to arrive at their destination before they left. The faster-than-light traveler could potentially influence events that occurred before their journey began. To understand this concept, imagine space-time as a vast landscape where different locations represent different points in space and time. In our normal experience, we can only move through this landscape in one direction through time, always heading toward the future. Light speed represents a boundary in this landscape, a cosmic barrier that separates the possible from the impossible. But if that barrier could somehow be crossed, The geometry of space-time itself suggests that new pathways would become available, routes that lead not just to distant places, but to distant times. The traveler might be able to take shortcuts through the fabric of reality itself, arriving at their destination before light from their departure point could reach it. Consider a hypothetical scenario where a spacecraft could travel at twice the speed of light. If such a vessel left Earth and traveled to a star 10 light-years away, it would arrive in 5 years. But here's where the situation becomes paradoxical. From the perspective of observers on Earth, the spacecraft would arrive at the star 5 years before the light from its departure could reach the star. In a sense, the spacecraft would arrive before anyone at the destination could see it leave. But the paradoxes don't stop there. If the faster-than-light traveler could somehow communicate back to Earth instantaneously, they could potentially send a message that arrives before they left. This would create what physicists call a closed time-like curve, a pathway through space-time that loops back on itself. Such curves could theoretically allow information, and potentially matter, to travel into its own past. The implications for aging become even more bizarre when we consider faster-than-light travel. If traveling at near light speed slows aging, what would happen to the aging process at speeds faster than light? The mathematical equations that describe time dilation become imaginary numbers when applied to faster-than-light motion, suggesting that we're entering a realm where our normal concepts of time and aging break down completely. Some interpretations suggest that faster-than-light travel might reverse the aging process entirely. A traveler moving faster than light might grow younger rather than older, their biological processes running backwards through time. They could theoretically return from their journey younger than when they left, having experienced negative aging during their voyage. But this raises profound questions about the nature of memory, consciousness, and identity. If your biological processes are running backwards, do you experience life in reverse? Do you remember things before they happen and forget them after they occur? Would consciousness itself flow backwards? Or would you experience some strange hybrid state where memory and anticipation become confused? The grandfather paradox illustrates some of the logical problems with backward time travel. If you could travel to the past and prevent your own birth, you would create a logical contradiction. You couldn't exist to make the trip if you prevented your own existence. This paradox suggests that either backward time travel is impossible, or the universe has some mechanism for preventing paradoxes from occurring. Some physicists have proposed that the universe might be self-consistent, automatically preventing paradoxes through quantum mechanical effects. In this view, any attempt to change the past would be thwarted by quantum uncertainties that conspire to maintain the consistency of the timeline. You might travel to the past, but you would find yourself unable to change anything in a way that would create a paradox. Another possibility is the many worlds interpretation, which suggests that traveling to the past would create a new timeline or alternate universe. In this scenario, you could change the past, but you would be changing a different timeline than the one you came from. Your actions would create a branching universe where events unfold differently, but your original timeline would remain unchanged. The concept of closed time-like curves opens up even more exotic possibilities. These are paths through space-time that loop back on themselves, potentially allowing objects or information to become their own cause. A traveler following such a curve could theoretically encounter earlier versions of themselves, creating loops of causality that challenge our understanding of free will and determinism. Einstein himself was deeply troubled by these implications of his own theories. He once wrote to a friend that the possibility of closed time-like curves made him doubt whether his theory of general relativity could be correct. The idea that the future could influence the past seemed to violate everything we understand about the logical structure of reality. Modern physicists have continued to grapple with these paradoxes. Some have proposed chronology protection mechanisms that would prevent the formation of closed time-like curves. Others suggest that quantum effects would make time travel impossible at the macroscopic scale, even if it's allowed by the equations of general relativity. The energy requirements for faster-than-light travel, if it were possible, would likely be even more enormous than those required for light-speed travel. Just as approaching light speed requires infinite energy, exceeding light speed might require energies that are not just large but complex or imaginary, quantities that have no clear physical meaning. There's also the question of what faster-than-light travel would do to matter itself. The equations of special relativity suggest that objects moving faster than light would have imaginary mass, a concept that physicists don't know how to interpret physically. Would such objects still be made of ordinary matter, or would they become something fundamentally different, existing in a realm beyond our normal understanding of physics? The relationship between faster-than-light travel and aging becomes even more complex when we consider that time itself might become a navigable dimension. If a traveler could move freely through time, they might be able to choose their age arbitrarily by traveling to different points in their own timeline. They could visit their youth, experience their old age, and return to any point in between at will. Such a traveler would exist outside the normal flow of time, able to witness the entire span of their life from an external perspective. They could potentially optimize their existence by spending more subjective time during pleasant periods and less during difficult ones. They might accumulate wisdom and experience from their entire lifetime and then return to youth with all that knowledge intact. But this godlike control over aging and time would come at an enormous cost. Being capable of time travel would be fundamentally separated from the normal flow of causality that gives meaning to choice and consequence. Their actions would have no permanent consequences because they could always travel back and change them. The narrative structure that gives meaning to life would collapse into a meaningless loop of infinite revision. The possibility of time travel also raises questions about free will and determinism. If the future already exists and can be visited, does that mean our choices are predetermined? Are we free agents shaping our destiny, or are we simply following a script that has already been written in the fabric of space-time itself? Some interpretations of time travel suggest that free will might be preserved through quantum indeterminacy. Even if the broad outlines of the future are fixed, quantum effects might preserve some element of genuine choice and uncertainty. The universe might be deterministic at large scales, while remaining unpredictable at the quantum level. The exploration of time travel takes us far beyond the original question of aging and light speed, into territory where physics and philosophy intersect in profound ways. The possibility that the universe might allow travel through time, whether into the future through time dilation or into the past through exotic mechanisms, challenges everything we think we know about the nature of existence. While faster-than-light travel and backward time travel remain highly speculative, the very fact that our best theories of physics don't definitively rule them out suggests that the universe may be far stranger than we currently imagine. The relationship between motion, time, and aging that we've been exploring opens doorways to possibilities that would have seemed like pure fantasy just a century ago. As we continue our journey through these cosmic mysteries, we're reminded that the universe operates according to principles that often defy our intuition and challenge our deepest assumptions about reality. The question of whether we could slow or reverse aging through manipulation of space-time remains open, pointing toward futures that may be more extraordinary than anything we can currently imagine. As we drift deeper into our cosmic contemplation, we must ask ourselves a more grounded question. Setting aside the theoretical impossibilities and mathematical barriers, what would it actually be like for a human being to attempt to live at or near the speed of light? The practical challenges of such an existence stretch far beyond physics and engineering into the realm of biology, psychology, and the fundamental nature of what it means to be alive. The first and perhaps most daunting challenge would be the simple matter of survival during the acceleration phase. The human body, evolved over millions of years to function in Earth's gentle gravitational field, is remarkably fragile when subjected to extreme forces. Even the moderate accelerations experienced by astronauts during rocket launches can be dangerous, requiring careful monitoring and specialized equipment to prevent loss of consciousness or injury. To reach any significant fraction of light speed within a reasonable time frame would require sustained accelerations far beyond anything the human body could endure. Consider that a typical car crash might subject a person to forces of 10 to 20 times Earth's gravity for just a fraction of a second, and such forces are often fatal. To reach even 10% of light speed within a year would require continuous acceleration of about 3,000 times Earth's gravity. No biological tissue could survive such forces. Bones would be crushed instantly, blood would be unable to circulate, and the brain would be compressed beyond the point where consciousness could be maintained. Even if we could somehow protect the body mechanically, the fundamental chemistry of life depends on delicate molecular structures that would be destroyed by such extreme accelerations. This suggests that any practical approach to high-speed space travel would need to involve much gentler accelerations spread over much longer periods. But this creates its own set of challenges. An acceleration of one Earth gravity, which would feel comfortable to space travelers, would require about 11 months to reach 10% of light speed, and over 3 years to reach 30% of light speed. For the duration of this acceleration phase, the travelers would need to survive in the harsh environment of space, while their spacecraft gradually approached these incredible velocities. The space environment itself presents numerous hazards that become more severe at high speeds. Even at moderate velocities, spacecraft must be protected from micrometeoroids, tiny particles of dust and debris that pepper interplanetary space. At near light speeds, even the smallest particle would impact with devastating energy. A grain of sand hitting a near light speed spacecraft would release energy equivalent to a large explosion. The interstellar medium, which seems empty from our Earthbound perspective, actually contains about 1 hydrogen atom per cubic centimeter. At light speed, each of these atoms would strike the spacecraft with tremendous force. The cumulative effect of billions of such impacts per second would create a form of cosmic sandblasting that would erode any known material. The spacecraft would need shielding so massive and sophisticated that it might constitute the majority of the vehicle's mass. But perhaps even more challenging than physical particles would be the electromagnetic radiation that fills space. The cosmic microwave background radiation, a faint echo of the Big Bang that permeates the entire universe, would become a serious hazard for near light-speed travelers. Due to relativistic effects, this normally harmless radiation would be blue shifted to much higher energies, potentially becoming lethal gamma radiation. At 90% of light speed, the cosmic microwave background would be shifted to X-ray energies. At 99% of light speed, it would become hard gamma radiation capable of killing a human being in minutes. The faster the spacecraft travels, the more intense this radiation would become, creating a fundamental barrier to survival at extreme speeds. The spacecraft would need massive radiation shielding to protect its occupants, but this shielding would add enormous mass to the vehicle, making it even more difficult to accelerate to high speeds. The radiation environment would also interfere with electronic systems, potentially making it impossible to maintain the complex life support systems necessary for human survival. Even if these physical challenges could be overcome through advanced technology, the psychological and social aspects of near light-speed travel would present equally formidable obstacles. The time dilation effects that could slow aging would also create profound isolation from the rest of humanity. A traveler on a high-speed journey would become unstuck in time, experiencing a different rate of temporal flow than everyone they had ever known. Communication with Earth would become increasingly difficult as the spacecraft approached light speed. Radio signals traveling at light speed would take longer and longer to reach the travelers as they journeyed to distant stars. More problematically, the signals would be severely red-shifted due to the relative motion, making them increasingly difficult to detect and decode. The travelers would gradually lose contact with human civilization, watching helplessly as years, decades, and eventually centuries passed on Earth, during what felt like much shorter periods of subjective time. They would become witnesses to the rise and fall of generations, unable to participate in the ongoing story of human development. The psychological impact of such isolation could be devastating. Humans are fundamentally social creatures, dependent on connection with others for psychological health and a sense of meaning. A crew isolated in space for what they experience as years, while knowing that much longer periods are passing for everyone they have ever cared about, would face unprecedented challenges to their mental health. The small, closed environment of a spacecraft would intensify these psychological pressures. Even the largest conceivable starship would be tiny compared to Earth, offering limited space for privacy, recreation, and the natural environments that humans find psychologically restorative. The crew would be trapped together in close quarters, with no possibility of escape or outside intervention if conflicts arose. The question of life support during such journeys presents its own set of practical challenges. A near light-speed voyage to even the nearest stars would require decades or centuries of subjective time for the travelers. During this entire period, they would need air to breathe, water to drink, food to eat, and waste disposal systems to maintain a habitable environment. Creating truly closed-loop life support systems that could operate reliably for such extended periods would require technological advances far beyond our current capabilities. Every component would need to function perfectly for decades without possibility of repair or replacement using outside resources. The system would need to recycle air, water, and organic waste with near-perfect efficiency, while maintaining proper atmospheric composition and pressure. The psychological stress of depending completely on artificial life support systems for such extended periods could be overwhelming. A single system failure could doom the entire crew, creating constant anxiety about the reliability of their technological cocoon. The knowledge that they are completely dependent on machinery for survival, with no possibility of rescue or evacuation, would weigh heavily on the travelers' minds. Food production during the journey would present particularly complex challenges. Carrying enough stored food for a multi-decade journey would require enormous cargo capacity, adding mass that would make the spacecraft harder to accelerate. Growing food during the journey would require sophisticated hydroponic or aeroponic systems, along with artificial lighting and climate control. These systems would need to operate flawlessly for the entire duration of the voyage. The question of reproduction and family formation during such journeys adds another layer of complexity. If the voyage lasts decades of subjective time, crew members might wish to form relationships, marry, and have children. But bringing children into the confined artificial environment of a spacecraft, with no possibility of ever experiencing natural environments or normal human society, raises profound ethical questions. Medical care during the journey would be another critical challenge. The crew would need to be prepared to handle any medical emergency that might arise during decades of travel, from simple injuries to complex surgical procedures. They would need medical equipment, medications, and expertise sufficient to handle any health problem that might occur, with no possibility of consultation with specialists on Earth or evacuation to advanced medical facilities. The aging process itself, even if slowed by time dilation, would continue throughout the journey. Crew members who begin the voyage as young adults might arrive at their destination as elderly people, having spent their entire adult lives in the artificial environment of the spacecraft. The psychological impact of aging in such isolation, without the normal social supports and life transitions that give meaning to different life stages, could be profound. The question of leadership and governance during such journeys would also be critical. Traditional forms of government and social organization might not work in the unique environment of a generation ship. The crew would need systems for making decisions, resolving conflicts, and maintaining social order during decades of close confinement. The return journey, if one were planned, would present all of these challenges over again, along with the additional psychological burden of knowing that even more time would pass on Earth during the return voyage. A crew that left Earth expecting to return to their home world might find themselves returning to a civilization so far advanced that they would be like visitors from an ancient past. Perhaps most challenging of all would be the question of purpose and meaning during such a journey. What would motivate human beings to endure decades of isolation, danger, and hardship for the sake of a journey to another star? The scientific knowledge gained might not justify the enormous human cost, especially considering that unmanned probes could gather much of the same information without risking human lives. The practical challenges of living at near light speed thus extend far beyond the physics and engineering problems we've already discussed. They encompass fundamental questions about human nature, social organization, and what makes life worth living. The dream of slowing aging through high-speed travel, while theoretically possible, comes with practical costs that might make it a cure worse than the disease it seeks to address. As we contemplate these realities, we begin to appreciate that the question of light speed, travel, and aging isn't just about conquering time, but about what we're willing to sacrifice in the pursuit of extended life. The universe may offer us ways to slow the aging process, but it extracts a price that challenges everything we value about human existence. As we approach the deeper mysteries of our cosmic journey, we find ourselves confronting questions that extend far beyond physics and biology into the realm of philosophy and the fundamental meaning of existence itself. The possibility of slowing or stopping aging through light-speed travel forces us to examine our most basic assumptions about life, death, time, and what it truly means to be human in a universe where the very flow of time can be manipulated. The prospect of dramatically extended life through time dilation raises profound questions about the nature of mortality and its role in giving meaning to human existence. Throughout history, the knowledge that our time is limited has been one of the driving forces behind human creativity, love, ambition, and the urgency with which we pursue our goals. If we could slow aging to a crawl, living for what amounts to thousands of years while the universe ages around us, would life retain its meaning and intensity? Consider how the brevity of human life shapes our values and priorities. We treasure moments with loved ones, partly because we know such moments are finite. We feel urgency about accomplishing our goals because we have limited time to achieve them. We appreciate the changing seasons, the passage of years, and the milestones of life, partly because they mark the progression of our brief journey through time. A being whose aging has been slowed by time dilation would experience a fundamentally different relationship with time and mortality. They might live subjective decades, while millennia pass in the outside universe. From their perspective, they would age normally and eventually die, but their lifespan would encompass vast stretches of cosmic time. They would become witnesses to the rise and fall of civilizations, the birth and death of stars, and perhaps even the evolution of life itself on distant worlds. This extended perspective might grant a form of cosmic wisdom impossible to achieve in a normal human lifespan. Such a being could accumulate knowledge and experience across astronomical timescales, developing insights into the nature of existence that no ordinary human could attain. They might become living libraries of cosmic history, carrying within their memories the stories of entire civilizations. But this cosmic perspective might come at the cost of human connection and emotional depth. How would such a being form meaningful relationships with others? Everyone they met during their journey would age and die while they remained essentially unchanged. They would be forever saying goodbye, watching friends and loved ones fade into the past while they continued their eternal voyage through space and time. The psychological impact of such radical longevity is difficult to imagine. Human consciousness and identity are shaped by the expectation of a limited lifespan. Our sense of self develops through the progression of life stages, from childhood through adulthood to old age. Each stage brings its own challenges, insights, and forms of growth. But what would happen to human development and identity formation if these stages were stretched across centuries or millennia? A near light-speed traveler might spend subjective decades in what would normally be considered the prime of life, experiencing the same physical and mental capabilities for extended periods. Would such constancy be a blessing, allowing for unprecedented achievements and experiences? Or would it become a form of psychological prison, trapping the individual in a single life stage without the growth and change that comes from aging? The question of memory becomes particularly complex when considering such extended lifespans. Human memory is not perfect, and perhaps this limitation serves an important function. We forget painful experiences, allowing emotional wounds to heal over time. We retain the essential lessons of our experiences while letting go of unnecessary details. But a being living for thousands of years would accumulate memories far beyond the normal human experience. Would such a traveler remember every moment of their extended journey, carrying the weight of countless experiences and losses? Or would their memories fade and blur like those of ordinary humans, leaving them with only fragments of their vast lifetime? The choice between perfect memory and forgetfulness both present their own challenges. Perfect memory might become overwhelming, while forgetfulness might rob the extended life of its accumulated wisdom. The concept of personal growth and development also becomes complex when viewed across such extended timescales. Normal human development is tied to the biological and social processes of aging. We mature emotionally and intellectually as our bodies and brains develop, and we continue to grow through the accumulated experiences of a normal lifespan. But what kind of development would be possible across centuries or millennia? A near light-speed traveler might have opportunities for learning and growth that no human has ever experienced. They could master numerous fields of knowledge, develop skills to levels of expertise impossible in a normal lifetime, and gain perspectives that span vast reaches of space and time. They might become Renaissance individuals of unprecedented scope, combining the knowledge of multiple civilizations and eras. Yet this growth might also become stagnant. After centuries of experience, would there still be new things to learn, new ways to grow? Would the traveler eventually reach a plateau of development beyond which no further growth is possible? Or would the vast scale of the universe always provide new frontiers for exploration and understanding? The question of purpose becomes equally complex. What would motivate a being to continue existing across such vast timescales? Normal human purposes, achieving career success, raising a family, contributing to society, become problematic when stretched across cosmic time. The societies and civilizations that give context to human achievement would rise and fall while the traveler continued their journey. Such a being might need to find purpose in cosmic rather than human terms. They might see themselves as guardians of knowledge, carrying the accumulated wisdom of vanished civilizations to new worlds and new species. They might view their extended existence as an opportunity to witness and understand the universe in ways impossible for shorter-lived beings. But there's also the possibility that purpose and meaning might become elusive across such timescales. The frameworks of meaning that sustain ordinary human life, religion, philosophy, social connection, personal achievement, might prove inadequate for a being whose existence spans geological eras. The traveler might face a form of existential crisis unprecedented in human experience. The relationship between individual identity and continuity also becomes problematic. Are you the same person after centuries of experience and change? Normal human identity is maintained through a combination of physical continuity, memory, and gradual change over time. But across centuries, even gradual change could accumulate into fundamental transformation. A traveler who began their journey as a young adult might, after centuries of experience, have perspectives, knowledge, and ways of thinking so different from their original self that they could be considered a different person entirely. Yet from their own perspective, they would experience continuity of consciousness and memory. The question of whether they remain the same individual becomes not just philosophical but practically important for questions of responsibility, relationships, and personal meaning. The concept of free will and determinism takes on new dimensions when considered across cosmic timescales. A being with access to vast stretches of time might develop perspectives on causality and choice that ordinary humans cannot comprehend. They might see patterns and connections invisible to shorter-lived beings, potentially gaining insights into the deterministic versus random nature of existence. Yet this cosmic perspective might also highlight the limitations of individual agency. A single being, no matter how long lived, remains a tiny part of a vast universe governed by forces beyond their control. The extended perspective might emphasize human insignificance rather than importance, leading to feelings of cosmic loneliness and powerlessness. The question of death itself becomes complex for such beings. They would still be mortal in the sense that their biological processes would eventually cease, but their experience of mortality would be fundamentally different. Death would come not after decades, but after millennia of existence. The approach of death might be visible across centuries rather than years, allowing for unprecedented preparation and contemplation. But would such a death be meaningful in the same way that normal human death is meaningful? The significance we place on death is partly related to its relative unpredictability and the brevity of life. A death that comes after thousands of years of existence might feel more like a natural conclusion than a tragic interruption. The possibility of returning to Earth after such a journey raises additional existential questions. A traveler who left Earth as part of one civilization might return to find a world so changed that it's essentially alien. The return might not be a homecoming, but an encounter with a foreign world populated by beings who, while technically human, might have evolved beyond recognition. Such a traveler would be a living fossil, a representative of an ancient era, attempting to integrate into a vastly advanced future. They might find that their extended lifespan, rather than being an advantage, has made them obsolete. The knowledge and perspectives they accumulated during their journey might be irrelevant to the needs of a civilization that has developed beyond their comprehension. The ethical implications of choosing such an existence are also profound. Is it moral to separate oneself so completely from the normal human experience? Does the pursuit of extended life through time dilation represent a form of selfishness, an attempt to avoid the common fate that all other humans must face? Or is it a noble quest for knowledge and experience that could benefit all of humanity? The choice to embark on near light-speed travel with its time dilation effects would be irreversible. Once begun, the journey would separate the traveler from normal human society in ways that could never be undone. This raises questions about informed consent and whether anyone can truly understand the implications of such a choice before making it. As we contemplate these philosophical depths, we begin to see that the question of slowing aging through light-speed travel is not just about extending life, but about fundamentally transforming the nature of human existence. The universe may offer us ways to cheat death and stretch our lifespans across cosmic timescales, but it extracts a price that goes to the very heart of what it means to be human. The dream of conquering aging through manipulation of time and space thus becomes a mirror in which we can examine our deepest values and assumptions about life, death, and meaning. It forces us to ask not just whether we can slow aging, but whether we should, and what we might lose in the process of gaining extended life. As we near the end of our cosmic journey through the mysteries of light speed and aging, we turn our gaze toward the horizon of human possibility. What does the future hold for our species as we continue to probe the deepest secrets of space and time? While the dream of light-speed travel may remain beyond our reach for generations to come, the pursuit of that dream is already transforming our understanding of the universe and opening pathways to discoveries we can barely imagine. The quest to understand time dilation and its effects on aging has led to remarkable advances in our comprehension of fundamental physics. Every experiment that confirms Einstein's predictions about the relationship between speed and time brings us closer to a complete understanding of the cosmic laws that govern reality. These insights are not merely academic curiosities but practical knowledge that could revolutionize technology and human capability in ways we're only beginning to appreciate. Current research in quantum mechanics and relativity is revealing new possibilities for manipulating space and time that go beyond conventional propulsion. Scientists are exploring concepts like quantum entanglement, which allows particles to influence each other instantaneously across vast distances, potentially opening new avenues for faster-than-light communication, if not travel. While these phenomena don't directly allow for light-speed travel, they suggest that the universe may contain mechanisms for transcending the apparent limitations of space and time. The development of increasingly powerful particle accelerators is providing new insights into the behavior of matter at extreme speeds. These facilities, while designed primarily for basic research, are teaching us how to handle and control matter moving at significant fractions of light speed. The engineering challenges involved in building and operating these accelerators are developing technologies that could eventually be scaled up for space propulsion systems. Advances in materials science are creating substances with properties that would have seemed magical just decades ago. Metamaterials with negative refractive indices, superconductors that operate at increasingly high temperatures, and carbon nanotubes with extraordinary strength-to-weight ratios are expanding the realm of engineering possibility. Future materials might possess properties that make previously impossible propulsion concepts feasible. The field of theoretical physics continues to explore exotic possibilities that could circumvent the apparent barriers to light-speed travel. Research into extra dimensions, string theory, and quantum gravity is revealing that our universe might be far more complex and malleable than we currently understand. While these investigations remain highly speculative, they occasionally suggest mechanisms that could allow for faster-than-light travel without violating the fundamental principles of relativity. The concept of warp drives, inspired by science fiction but grounded in legitimate physics, continues to evolve as scientists refine their understanding of space-time manipulation. Recent theoretical work has reduced the energy requirements for such devices from the mass energy of Jupiter to potentially achievable levels, though they still require exotic matter that may not exist. Even if warp drives prove impossible, the research into their theoretical foundations is advancing our understanding of space-time in ways that could lead to unexpected breakthroughs. Advances in computer simulation and artificial intelligence are accelerating the pace of discovery in all areas of science. Complex models of space-time, particle interactions, and biological systems can now be simulated with unprecedented accuracy, allowing researchers to explore scenarios that would be impossible to test experimentally. These tools are helping scientists understand the detailed mechanisms of time dilation and its potential effects on biological systems. The growing field of synthetic biology is providing new insights into the aging process itself. Scientists are learning to engineer biological systems with properties that don't exist in nature, potentially including resistance to the cellular damage that causes aging. While this research doesn't directly address the time dilation approach to slowing aging, it could complement such approaches or provide alternative pathways to life extension. Space exploration itself is advancing rapidly, with private companies and government agencies developing increasingly sophisticated spacecraft and propulsion systems. While current technology is nowhere near capable of achieving significant fractions of light speed, each advancement in propulsion efficiency brings us incrementally closer to higher speeds. Ion drives, fusion rockets, and other advanced propulsion concepts could eventually enable spacecraft to reach speeds where time dilation effects become noticeable. The study of extremophiles, organisms that survive in conditions previously thought impossible for life, is expanding our understanding of the limits of biological resilience. Some of these organisms can survive intense radiation, extreme temperatures, and other conditions that spacecraft crews would face during high-speed interstellar travel. Understanding how these organisms achieve such resilience could inform the design of life support systems for future space missions. Developments in hibernation and suspended animation research, while still in early stages, could complement the time dilation approach to aging during space travel. If humans could be placed in states of suspended biological activity, the effective aging during long space journeys could be reduced even further. Combined with time dilation effects, such technologies could make interstellar travel feasible within human lifespans. The field of nanotechnology is developing tools for repairing cellular damage at the molecular level. Microscopic robots capable of repairing DNA, removing cellular waste products, and maintaining cellular function could potentially slow or reverse aging through direct intervention rather than time dilation. Such technologies could be particularly valuable for space travelers facing the accumulated damage of long journeys through the radiation environment of space. Advances in energy production and storage are addressing one of the fundamental barriers to high-speed space travel. Fusion power, which could provide vastly more energy per unit mass than current technologies, might make higher acceleration possible. Research into antimatter, production, and storage, while still in its infancy, could eventually provide the ultimate energy source for space propulsion. The development of increasingly sophisticated life support systems is making long-duration space missions more feasible. Closed-loop systems that can recycle air, water, and organic waste with high efficiency are reducing the mass requirements for extended missions. These systems could eventually become reliable enough to support the multi-decade journeys that would be necessary to reach significant fractions of light speed. Robotic and artificial intelligence technologies are becoming capable of tasks that previously required human presence. Advanced robots could potentially prepare destinations for human arrival, construct facilities, and even begin terraforming processes on distant worlds. This could reduce the burden on human crews during high-speed interstellar missions, allowing them to focus on survival during the journey rather than preparation for arrival. The growing understanding of genetics and epigenetics is revealing how environmental factors influence gene expression and aging. This knowledge could be applied to prepare space travelers for the unique stresses of high-speed travel, potentially using genetic modifications or epigenetic interventions to enhance their resilience to radiation, low gravity, and other space hazards. Quantum computing is beginning to tackle computational problems that are impossible for classical computers. As these systems mature, they could enable simulations of complex physical systems with unprecedented accuracy, potentially revealing new approaches to space propulsion or time manipulation that are not apparent with current computational tools. The search for extraterrestrial intelligence continues to expand, using increasingly sophisticated methods to detect signs of advanced civilizations. If such civilizations exist and have developed technologies for faster than light travel or time manipulation, detecting them could provide insights into how such technologies might be achieved. Even if direct contact proves impossible, observing the effects of their technologies could guide our own research efforts. International cooperation in space exploration is creating frameworks for ambitious, long-term projects that no single nation could undertake alone. The collaboration required for interstellar missions would likely exceed anything previously attempted, potentially fostering new forms of international unity and shared purpose. The challenge of reaching other star systems could become a unifying goal for all of humanity. The philosophical and ethical discussions surrounding life extension and time manipulation are helping society prepare for the moral complexities that such technologies would create. As we develop greater capabilities to extend life and manipulate time, we need frameworks for deciding how such technologies should be used and who should have access to them. Educational institutions are beginning to incorporate concepts of relativity, time, dilation, and space exploration into curricula at all levels. This is creating generations of students who think naturally about concepts that were once confined to advanced physics courses. These future scientists and engineers will approach the challenges of space exploration with intuitive understanding of relativistic effects and their implications. The inspiration provided by the dream of light-speed travel continues to motivate young people to pursue careers in science, technology, engineering, and mathematics. Even if the dream itself proves unattainable, the pursuit of it is advancing human knowledge and capability in countless ways. The technologies developed in pursuit of impossible goals often find unexpected applications that transform society in ways their creators never intended. As we look toward the future, we can imagine scenarios where humanity gradually develops the capability for increasingly high-speed space travel. Perhaps the first steps will be missions that achieve 1% of light speed, creating barely noticeable time dilation effects but proving that the concepts work in practice. These could be followed by missions reaching 5 or 10% of light speed, where time dilation becomes significant enough to provide real benefits for aging. Even if we never achieve true light speed travel, the journey toward that goal is already transforming our species. We are developing technologies, perspectives, and capabilities that would have seemed magical to previous generations. The quest to understand time, space, and aging is pushing the boundaries of human knowledge and opening possibilities that extend far beyond the original questions that motivated our exploration. The future of time and space exploration may not look exactly like the science fiction dreams of light-speed travel and stopped aging, but it promises to be no less extraordinary. As we continue to probe the deepest mysteries of the universe, we are not just seeking to extend our lives or travel to distant stars. We are discovering what it means to be conscious beings in a cosmos that is far stranger and more wonderful than we ever imagined. The dream of conquering aging through light-speed travel may remain forever beyond our reach, but the pursuit of that dream is already transforming us into something greater than we were before. In seeking to transcend the limitations of time and space, we are transcending the limitations of our own understanding and capability. The journey itself, regardless of its ultimate destination, is making us more than human. As our cosmic journey through the mysteries of light, time, and aging comes to a gentle close, we find ourselves back where we began, floating peacefully in the vast darkness of space, surrounded by the eternal dance of stars and galaxies. The questions we've explored tonight, about whether we could stop aging by traveling at the speed of light, have taken us on an extraordinary voyage through the deepest principles that govern our universe. We've discovered that time, which seems so constant and unchanging in our daily lives, is actually one of the most flexible and mysterious aspects of reality. Einstein's revelations showed us that time can stretch and compress, that it flows differently for travelers moving at high speeds, and that the aging process itself is intimately connected to the fabric of space-time. The faster you move through space, the slower you move through time, and with it, the slower all the biological processes that make up aging. The mathematics are clear, and the physics well established. If somehow we could approach the speed of light, we could indeed slow down aging dramatically. A traveler moving at 99% of light speed would age about 7 times more slowly than people at rest. At 99.9% of light speed, they would age about 22 times more slowly. The dream of using speed to slow aging isn't science fiction. It's a direct consequence of the fundamental laws that govern space and time. Yet, as we've seen, the universe seems to protect itself from beings who would manipulate time too dramatically. The energy requirements for reaching light speed are infinite, creating an absolute barrier that no amount of technology appears capable of overcoming. The practical challenges of surviving the journey, from deadly acceleration forces to cosmic radiation, present obstacles that may be equally insurmountable. But perhaps most profoundly, we've discovered that the question of slowing aging through light-speed travel isn't really about aging at all. It's about what it means to be human, to live a meaningful life, to form connections with others, and to find purpose in our brief existence. The cosmic loneliness that would accompany such a journey, the separation from the normal flow of human time, and the transformation of consciousness across vast timescales might make extended life a burden rather than a blessing. The twin paradox we explored reveals the heart of this cosmic mystery. While the traveling twin returns younger than their earthbound sibling, they have also lost something irreplaceable: the shared experience of time passing, the common rhythm that binds all human lives together. They gain years but lose connection, achieve longevity but sacrifice belonging. Our exploration has shown us that aging isn't just a biological process to be conquered, but an integral part of the human experience. The knowledge that our time is limited gives urgency to our choices, meaning to our relationships, and poignancy to our achievements. The very brevity of life that we sometimes lament may be essential to what makes us human. Yet the journey we've taken tonight has been far from futile. In exploring the impossible dream of light-speed travel, we've gained profound insights into the nature of time, space, and existence itself. We've seen how the universe operates according to principles far stranger and more beautiful than our everyday experience suggests. We've discovered that reality is both more constrained and more flexible than we imagined. The pursuit of light-speed travel, even if it remains forever beyond our reach, continues to drive scientific discovery and technological advancement. The quest to understand time dilation has led to the development of GPS satellites that must account for relativistic effects. Research into high-energy physics has given us medical imaging technologies, cancer treatments, and communication systems. The seemingly impossible dreams of today often become the practical realities of tomorrow. Perhaps most importantly, our cosmic journey has reminded us that we are part of something magnificent and mysterious. We are conscious beings capable of contemplating the deepest laws of physics, of imagining journeys to distant stars, and of asking profound questions about the nature of time and existence. In a universe vast beyond comprehension, we have somehow emerged as entities capable of understanding that vastness. The stars that surround us as we rest in the cosmic darkness have been shining for billions of years. They have witnessed the birth of galaxies, the formation of planets, and the emergence of life. Some of these stars have already died, their light only now reaching us across the vast distances of space. We are seeing them not as they are, but as they were, observing the past through the present, traveling through time simply by looking up at the night sky. This natural time travel, achieved not through impossible speeds but through the simple fact that light takes time to cross space, reminds us that we are already time travelers in our own way. Every moment we experience is slightly in the past by the time light from it reaches our eyes. Every star we see is a window into history, a connection to distant times and places. The question of whether we could stop aging by hitting light speed has led us to contemplate the fundamental nature of time, the meaning of mortality, and the value of our brief existence in the cosmic scheme of things. We may never travel at the speed of light, but we have traveled through ideas and concepts that expand our understanding of what it means to be alive in this extraordinary universe. As you settle into rest tonight, carried along by Earth's gentle motion through space at thousands of kilometers per hour, remember that you are already a space traveler. You are riding a planet that orbits a star that moves through a galaxy that dances through an expanding universe. You are part of a cosmic ballet that has been unfolding for nearly 14 billion years, and you will continue to be part of it for whatever time remains to you. The aging process that we've examined so thoroughly tonight continues in your body, even as you rest. Your cells are working to repair the day's damage. Your brain is processing the day's experiences into memories, and your heart continues its steady rhythm that marks the passage of your personal time. This is the miracle of biological existence, the complex dance of chemistry and physics that maintains your consciousness and carries you forward through time. Whether we ever solve the mysteries of light-speed travel and its effects on aging, we have already been granted something extraordinary, the gift of awareness in a universe that seems designed for consciousness to emerge and contemplate its own existence. We are the universe becoming aware of itself, matter organized in such a way that it can ponder the laws that govern matter. The cosmic perspective we've gained tonight, seeing ourselves as part of the vast sweep of space and time, can bring both humility and wonder. We are incredibly small in the cosmic scheme of things, yet we are also incredibly significant as conscious beings capable of understanding our place in that scheme. We may age and die in what amounts to an instant in cosmic time, yet we are capable of achievements and insights that resonate across ages. So rest now under the patient stars, knowing that you are part of something magnificent. Whether time dilation ever allows humans to slow their aging, you have tonight explored ideas that stretch your mind across the cosmos and connect you to the deepest mysteries of existence. The questions we've pondered about light speed and aging have revealed truths about time, space, and consciousness that make your brief life infinitely more meaningful. In the end, the greatest journey isn't through space at impossible speeds, but through the landscape of ideas and understanding that makes us uniquely human. Tonight you have traveled farther than any spacecraft, exploring concepts that span the universe and illuminate the nature of reality itself. Sweet dreams, fellow cosmic traveler, and may your rest be filled with the wonder of all we've discovered together in our journey through the stars.